Good afternoon, everyone. My name is Ian Johnson.
I'm Chris Fong.
I'm Ivan Tapia.
Steve Trebillion.
And we are part of the Torsion test sub-team for the Spartan Superway ATN. So what are some of the problems facing our transportation system today? For one, it's dirty. As you can see from this graphic, in 2013, the EPA estimated that 27% of the U.S.'s total greenhouse gas emissions came from the transportation sector. And within this, the U.S. Climate Action Report from 2014 found that in 2011, 41.2% of all transportation greenhouse gas emissions came from passenger vehicles, and 17.4% came from light-duty trucks. So it's obvious that automobiles are a major factor causing global pollution and climate change. And another factor is that it's inefficient. So recently the expanding job market in the Bay Area has caused an increase in traffic during rush hour times. So according to the U.S. Census Bureau in 2009, the average American spent 25.1 minutes per commute session to get to where they needed to go. And we estimated that out to be about 217.5 hours per year. And so this is a lot of time wasted that could have been more productive for workers. And also it increases the use of petroleum, which in turn increases greenhouse gas emissions. And the third point is that it's dangerous. So to illustrate this, over the period of September 19th to 26th this year, there were 5 fatal car accidents within the Bay Area. So this kind of illustrates the dangers of cars when automobiles, trains, light rails, trucks, they all kind of share the same space. There's bound to be accidents that happen. And and you take into account factors such as drunk drivers, road work, poor weather conditions, and the dangers of driving increases. So what is the solution to these problems? The solution is Spartan Superway. So one of the main goals of Spartan Superway is to get vehicles off the roads. So this will, by using elevated tracks. So this will reduce the density of the traffic congestion on the roads, which leads to more safe commuters and also lessening traffic. And it's also completely renewable and sustainable because it's 100% solar powered. So this will limit the impact of climate change, reduce our reliance on petroleum, and lessen the amount of pollution in the air due to emissions from vehicles. So what is the Torsion test sub-team, and how does it kind of factor into the overall scope of the project? So the goal of the Torsion test sub-team is to design, FEA model, and torsion test a full-scale 5-foot section of the guideway. And so this is to ensure that it behaves as expected when under a torsional load. And then the significance of this for the overall project is that it will allow for the development of new track sections such as switching sections, turns, and elevation changes. And it will also allow future Spartan Superway teams to work more efficiently so that they'll know the final design of the track. And so now I'm going to pass it off to my colleagues, and they'll give you a few more details about Torsion test sub-team.
So I researched a bunch of different rail transit lines that I found to be not similar, but appropriate to compare to. The first one on the left is the Ultra, which is an urban light rail transit. It's a bottom rail KRT or personal rail transit at the Heathrow Airport in London. The second one is the Siemens People Mover, or the H-Bahn, and that's located in Dortmund, Germany, on the Dortmund College campus. And the third is actually a new development by NASA. It's called the Skytrain, and they actually propose it to be installed in the San Jose area. The Ultra has proven itself as a success at the Heathrow Airport in London. As you can see, it's bottom mounted, so it doesn't really apply to our torsion test design. But I thought it was important to mention that it does have offline stations like ours, and it's more easily installed since it's bottom mounted. You can install it like in more places than you would here, because you'd have to build structures for our design. It was found that 90% of requested rides were available immediately after request, and all features were rated as excellent or good by the people that used it. The H-Bahn, or the People Mover, this was in Dortmund, Germany. Benefits is it's good for what it's used for, which is a college campus, a very large college campus. But it's not a personal rapid transit system. It's actually more of a busing system. There are only 3 or 4 cabins in use at a time, and each cabin arrives about every 10 minutes. Sorry. The drawbacks are the proposed extensions to the network are not currently cost effective since it's so wide, and it's just not a PRT, so it doesn't really apply to ours. But it is a hanging rail system. The third one is the Skytrain. It's a personal rapid transit network designed by NASA, but it's not yet implemented. It's expecting its first construction in Israel, France, and India at the end of this year. The benefits are that it's sleek and efficient. The trams themselves are very lightweight, so they require less energy to be moved. But this also means that there's no room to move around, and it's, as you can see, it's only for use for able-bodied people. It's kind of hard to get a wheelchair up this and a person inside the vehicle.
Alrighty, so this Gantt chart pretty much illustrates our goals for the semester. Initially, as we all started out with research, kind of researching what an ATN is, researching some of the past year's designs, also researching kind of ourselves to figure out whether we were in the proper subgroup that we wanted to be in, and we wanted to move forward with that. So we're still here, so we kind of figured that out. Next, after the research, we need to learn ANSYS. Part of being the torsion test team is that we're going to model it in ANSYS. None of us really are familiar with ANSYS, so kind of allotted a good amount of time, almost 2 months, to actually familiarize ourselves with the software, so we could move forward with that. Once we kind of at the same time, we're going to start doing some research on actually designing the guideway itself. Ultimately, with the CAD design, we want a physical geometric model of what we're actually dealing with. Basically, that's important because we're going to need that to be able to figure out which materials we need, which materials to use, how big, how much, and whatnot. As the previous group mentioned, we're going to need to collaborate with the other parts of the team. So we've got to communicate with the solar wayside team, the fail-safe team, the bogie suspension guideway team, just in case they made any changes to the actual overall design. That way we could implement that into our analysis moving forward. And then next, again, we want to finalize our model design. That way we can actually start the testing in ANSYS and be able to come up with some data for that. deliverables go, pretty straightforward. What we're going to have is just a lot of test data showing how the guideway will function under different types of torsions and whatnot. Now this is just going to be the modeled figure. We haven't actually ran it through the torsion tester here on campus, but that's going to be the following semester when we actually build it and whatnot. And then also a deliverable is going to be the actual CADed model. Basically, again, to kind of figure out what materials we need. Hopefully we could figure out what kind of pricing we're going to be looking at to actually build it, kind of come up with a game plan on how to move forward with the build.
So for functional specification, so I looked through the past reports and I couldn't really find anything on torsion testing or any calculations on it. And with this was I think in 2014, the one right behind us. I couldn't really find anything on that. And for the one we have here, there's really, like I said, there's not many calculations on it. And so it's going to be kind of a challenge for us to see where we're at. Maybe we have to test it first or run it through ANSYS and then see what we get. If we have to make any design adjustments, then we can do that accordingly. But that's going to be quite a challenge. Oh, and then so our project challenges. Project mentioned right now, but so we have to coordinate with other. I feel like kind of at the bottom of the totem pole. I mean, it's not necessarily true. Maybe all the sub-teams feel like that, but I guess our team kind of relies a lot on the other teams. We can't go forward unless we coordinate with the other teams. And then, as mentioned earlier, ANSYS is a very complex program, so that's one thing we have to try to learn it the best we can, so we can get good data. And then getting a material is going to be really one of our challenges. We still have to figure out how much it's going to cost, where we can get it from, and then welding. We might have to do some welding, so we need to get a welder or maybe take it to a shop that can help us out. So we still have a lot of planning.
So as far as team member responsibilities, I'm going to be serving as the lead project sub-team manager. So this will involve like contacting all the members of our sub-team, making sure everything is organized, that we're on schedule. And yeah, basically just like organizational aspects. And and then I'll be also serving as the calculations manager, which I'll be involved with all the hand calculations of, say, like fatigue analysis, like torsion and stresses. And then I'll also be serving as the lead communicator. So I'll be communicating with the other sub-teams just to see where they're at on their projects and how we can kind of incorporate, like have the same design and make everything kind of seamless. And also that means communicating with our mentors and also people that have been working on the guideway. Like there's a grad student named Kriti who has been working on optimizing the cross-section of the guideway for her senior project, or for her master's project thesis. And yeah, those will be my responsibilities.
And then I'll be taking over, kind of leading the ANSYS tests and whatnot, basically because I was the only one to really get it up and running on my computer, so I kind of just fell into that. Also, be helping out with scheduling. As Ron mentioned to us last week, or to some of us, that a schedule is something that we are accountable for keeping as far as the time frame goes. So keeping on schedule is a big deal, and making sure that we complete the tasks.
I'll be the editor, or I'll be the librarian and the editor. As a librarian, I'll be keeping track of all the files, like SolidWorks and the ANSYS files that we need, and I'll be organizing them for later use for maybe your teams or maybe next year's teams. I'll also be the editor of the writing that needs to be done for the final project proposal.
So I'm in charge of budgeting and expenses. So I have to find out how much money we have. I have to keep track of what we spend, and then I have to see where we can get more bang for our money. So wherever we can find maybe cheaper material without compromising the integrity of the project. And then I'm the lead for SolidWorks design, so I'm in charge of drawing it up on SolidWorks and making sure that we have all the drawings on time and correct.
And that's basically our sub-team, and we're going to open the floor for any questions right now.
So did you guys present your functional specifications?
So I guess I wasn't really sure what design we're going to use or what beam, so I looked at the past projects to see if we could like find anything on it, but I couldn't really find anything on torsion. And then I don't know if we have like a final design, or we still have to like rely on, we have to coordinate with other teams.
Let me give you some suggestions for yours. One is you kind of had it in there, it's got to be, say, 5 feet or less, right? Because it won't fit on the torsion testing. So that's your design work needs to be like that. Two, it's probably got to be, you kind of said it also needs to be faithful to the real design and all that. So those are things you want to kind of quantify as much as possible. Those are the things that, when you finally deliver it, we take out the tape measure and, can't fit in the machine, you blew it, right? Or 5 feet, yeah, it's right under 5 feet, it's going to work fine, right? So then you know you're successful enough. So try and quantify your functional specifications. As much as you know them, you'll know more as you go on.
Thank you.
So have you guys been in touch with Jake Parkhurst? You have all the files that he's generated so far?
I've not seen his files, but we have been able to see the files that Kriti supplied us with.
Full court press, get a hold of Jake, get a core dump of all his stuff, and make sure you have the current design from Banked. Got to be in contact with Banked as well.
Okay.
So start at that together.
Thank you.
Okay, good. So the first few, Ian and Chris, AE method, bang on, you guys nailed it, very good. Good insertion sentences, good graphics. A couple other, a little mixed than the others, maybe not having that, but learn from those two guys. I think you guys got it very well.
On that point, I'd like to say that where you had 2 or 3 assertions on a page, you could put a separate one on each page, and it helps, I think, the focus. So while you had the assertion, instead of showing 1, 2, 3, go give the assertion, maybe have 1, 2, 3, then zoom in on one, zoom in on the next, zoom in on the third, and then go forward. But don't clutter up an illustration with 3 different elements unless you're saying these 3 things are
Yeah, they're all together.
different types of horses. You've got a red horse, a brown horse, and a striped horse. Like a zebra.
Okay. Yeah, and following along with that, those are really good statistics, very powerful. So that's guys did some good research. And Steve did, I think, fantastic in being able to address, good volume. And you did a really good job of facing the audience. I think at the end, all 4 of you guys did well at saying what the responsibilities of getting eye contact. I had a little bit when your presentation kind of facing the screen. Everyone, when you make your presentation, you really want to do the sprinkler head. It hits everything. You're talking for your family. Don't be afraid. Got to get practice giving presentations, being incredible, because you get up in your job, you don't want to be cowering or turning away. It's people are kind of like, why aren't they looking? Why isn't he looking at us? So deliver here. It's good practice. Okay.
On that same point, if you're carrying a piece of paper, you don't know your material well enough. You really got to get immersed in your subject so that you don't have to rely on a piece of paper and you don't have to look at the screen. I mean, only long enough to know what the next slide is going to be. But once you've got the slide up, you know your material, deliver it to the audience, and you don't talk to the TV. Several, in the previous group too, a lot of people find it interesting to talk to the TV. The TV doesn't have doesn't have ears. It only has a speaker, only an output.
And I think, Steve, you could probably use some graphics to go along with those goals rather than speaking from the Gantt chart. That's good to have that and speak to it, but I think for some of the goals, if you had some graphics to go along, it would have been better.
Okay.
Anything else in this group? Didn't like. Okay?
You guys very the previous team were pretty ambitious and you're all jump into ANSYS and learn
Good.
Thank you for the feedback.
Okay.